Wanted to work through Fourier transform example for the damped-driven pendulum. This is the problem that we examined when we were solving ordinary differential equations. And we explored the motion of the damped-driven pendulum through plotting the displacement versus time, the angular velocity versus time. We also looked at phase space diagrams that are trajectories in the space of the angular displacement and the angular velocity of the pendulum. And we also looked at Poincare sections, which are stroboscopic points on the trajectory, the phase space trajectory, that are sampled either at the natural frequency of the pendulum or at the driving frequency of the pendulum, depending on the application. All those types of plots gave us a way of picturing, understanding, and exploring the damp-driven pendulum. The Fourier transform and the frequency domain are a further way of exploring the motion of the pendulum. And they're a very useful way, a very handy way of seeing some of the features of the damp-driven pendulum. In particular, the evolution from a single periodic motion through bifurcation period doubling, through multiple bifurcations and multiple period doublings towards chaos. So we're going to explore that a little bit with this new tool, with this new technique, which is the Fourier transformation. So here's my code for the damped-driven pendulum. And I just want to make a few remarks about it that are reminders, and just a few other remarks about it, about what I've added to the code. I've added to the libraries that we import the SciP library, because I'm going to use the function FFT that will perform a Fourier transform for us, and I'm going to use the function FFT frequency that's going to allow us to calculate the frequency axis of the frequency domain plots. So we're going to use those two functions. So I added these this library package. These are the parameters of the damp-driven pendulum, just as a reminder. I'm going to work with a damp-driven pendulum that has a natural frequency that's 1 radian per second. So I've set that through the parameters G and L. And then we'll be playing with the parameters associated with the damping force. Here I've got a small damping force. Beta is 0.1. And the driving force. Here I've got the driving force switched off. Alpha is 0. And then we'll play with these parameters. We'll explore first a little bit the frequencies that we see when we have a damped pendulum. And then we'll spend a bit more time where we explore the frequencies that we see when we have a driven pendulum. Here are the parameters that determine the discrete time that I'm going to follow the pendulum's motion over. So I'm going to follow the pendulum's motion for 100 periods, 100 cycles. So this might be 100 natural frequency periods if I'm doing the damped pendulum. This might be 100 driven periods if I'm doing the driven pendulum. And for those 100 periods, I'm going to make 20,000 discrete steps. So one cycle, one natural frequency cycle or one driving frequency cycle is going to correspond to 200 samples. So one sample is 1/200th of the driving period or the natural period. So this cell is where I compute the solution to the differential equation by calling the Runge-Kudder-4 method function that's going to calculate the solution and giving it an argument that describes the differential equation for the damped driven nonlinear pendulum. So the function is calculated here. The value of the angular displacement as a function of time, the value of the angular velocity as a function of time is calculated in this for loop here. To my code from earlier weeks where we were solving the differential equation, I've added the call to the function that's going to calculate the Fourier transform and also give us the frequency axis for the Fourier transform. That's these lines here. One thing I'm going to do, this is important for the case of the driven pendulum, is that I'm going to call the function after the transients are over. So I'm only going to calculate the FFT once we're in steady state. So you'll notice here that I slice the array theta such that I remove the transitory period, the transient period, and I just keep the steady state period so that I can explore that. The other thing you'll notice here, here's where I'm calculating the frequency spectrum in cycles per sample. So I can view the frequency distribution, view the data in the frequency domain in the language of cycles of the pendulum per sample. Remember, my samples are going to be 1/200th of either the natural period or the driving period. And then I make plots as before. Here are plots for the case of the damped pendulum that I'm going to make. So one of them is a familiar one to us for the damped pendulum. It's the phase space diagram. So horizontally is the angle and vertically is the velocity. And the green line is the phase space trajectory as the pendulum oscillates and dies off. And then the blue points are the Poincare section points. And you see they form a path from the initial conditions to the final equilibrium. The two other plots are the motion of the pendulum in the frequency domain. And so there's the plot in the middle here, which is the full frequency spectrum, and the lower plot here, which is an expanded frequency spectrum. So in the full frequency spectrum, I've got frequencies from 0 over here on the far left to the maximum frequency that I can see based on the Nyquist limit. And the maximum frequency that I can see based on the Nyquist limit is half a cycle per sample. It corresponds to a period of 2 samples. You can't see a smaller period if you sample at this rate. You can't see a higher frequency sampling at this rate. So this is the Nyquist limit. You'll notice that our damp-driven pendulum has a natural frequency that's way over here on the far left. And so I've expanded that region in the lower plot so that I can see the frequency of the pendulum. And this frequency here, if you look at it, it's about 0.005 cycles per sample. That means that it would take 200 samples to complete one period. And that's how I define the discrete time distribution, time array. It has 20,000 samples for 100 periods. So there's 200 samples per period, and 200 samples per period corresponds to this frequency of 0.005 cycles per sample. Okay, so now I'd like to move to some results of the calculation, and in particular, the results in the frequency domain. I've got this one slide here that describes the results for the damped pendulum, underdamped pendulum. And then I've got a couple more slides that describe the results that I got for the driven pendulum. In the damped case, we're just going to look at the effects on the frequency of the pendulum of the damping. And then in the driven case, we're going to look at those interesting effects related to period doubling, multiple period doubling, and finally chaos in the case of the driven pendulum. So on all the plots, this plot and the following plot, I've got 4 quadrants. I got the top left, top right, bottom left, bottom right. Each quadrant contains 3 plots. The upper plot in each quadrant is the phase space plot. And then the lower 2 plots are the frequency domain plots with the full scale from 0 to the Nyquist limit and with the expanded scale below that. So in this particular case, the top left plot has 0 damping, beta equals 0. The bottom left plot has a damping that's small, 0.1 for beta. And then on the right, the top right plot has an increased damping, and then the bottom right plot has a further increased damping. So what do we expect as we have a damped pendulum, an underdamped pendulum, beta is less than omega naught, and we're going to increase the damping? What we expect based on analytical analysis of the damped pendulum is that the frequency of the motion of the pendulum is going to decrease as we increase the damping. And there's an equation, it's upstairs here. For the natural frequency of the damped pendulum, that's omega d, in terms of the natural frequency of the undamped pendulum, that's omega here, and the damping parameter. And you can see here that omega d equals square root of omega squared minus beta squared. So as we increase beta, we're going to decrease omega d. Now, because of the squares, it's not a linear decrease in omega d with beta. When beta is really small, it barely has any effect. But when beta gets bigger, it starts to have, an increasingly large effect on the frequency of the damped pendulum. So let's look at the frequency plots, the frequency domain, and look for the frequency of the damped pendulum. So as a reference point, here's the frequency for the undamped pendulum, this sharp spike here. So this is omega naught, the natural frequency of the undamped pendulum, in the units of cycles per sample, 0.005 cycles per sample. When I switch on the parameter beta and set it to 0.1, here's the frequency spectrum. Here's the frequency domain distribution. So there's a big difference here. What was a spike, a single frequency, is now a broad peak. its central value looks to be almost the same as the natural frequency, and actually is in this case almost the same. Since beta is just 0.1, then if you calculate omega squared minus beta squared, take the square root of that, the damped frequency is different from the natural frequency, the undamped pendulum, by only 0.5%. So a very small effect. We can't even see it on this plot. On the right, we turn up the damping frequency further. We turn up the damping parameter further. We turn it up to 0.2 and then up to 0.5. In these cases, we see the reduction of the frequency of the damped pendulum compared to the frequency of the natural pendulum. So for a damping parameter of 0.2, the frequency of the damped pendulum is a couple of percent less than the natural frequency. We can see that in this plot here. And for a damping parameter of 0.5, the natural frequency of the damped pendulum is 14% less than the natural frequency of the undamped pendulum. We clearly see that here. So this is just an example of how in the frequency domain, those effects on the frequency of the damping, that the frequency of the pendulum is reduced by the damping, and secondly, the frequency distribution is broadened by the damping, are very clear on these plots. Okay, so now I'm going to move on to the driven pendulum, and we're going to look at the driven pendulum where I progressively increase the driving force. So I'm going to systematically increase the driving force. For these calculations, I set the natural frequency at 1 again, like the damped pendulum case. I'm going to set the driving frequency at 2/3 of the natural frequency. So that's common in all the plots, the graphs I'm going to show you. And I'm just going to be changing the amplitude of the driving force. And so I've annotated these plots with the amplitude of the driving force. So the plots follow the same pattern. I've got 4 quadrants. They're going to have different values of the driving force parameter, alpha. And then in each quadrant, we've got the phase space plot upstairs, and then the 2 lower plots are the frequency domain plots on the full scale and then an expanded scale. And so let's walk through each one of these. Let's start with the top left. Here, the driving force is relatively small. The driving parameter is 0.1. What do we see in this case? Well, we see in the phase space diagram a transient period, but then after a few oscillations, the pendulum just swings backwards and forwards in periodic motion at the period of the driving force. We can see this in particular. Here's the Poincare section points where I've eliminated the transient period, and they're just points that lie on top of one another, indicating that the pendulum in steady state is just executing periodic motion. In the frequency domain, what do I see? I just see a narrow spike at the frequency of the driving force. The driving force now has a frequency that is, its period is 200 samples. Its frequency is 0.005 cycles per sample. So this is just a lightly driven pendulum that's swinging backwards and forwards once in steady state at the applied natural frequency. In the plot below, so this is the bottom left, I've turned up the amplitude of the driving force from 0.1 to 0.9. What happens when you do that? Well, the main thing that happens in this particular step, increase of the driving force, is that you still go through that transient period. You still achieve simple periodic motion, and we can see that by the Poincare section points that are lying on top of one another. But it's no longer simply sinusoidal motion. With these larger amplitude oscillations due to the larger driving force, it's periodic motion, but not simply sinusoidal motion. And you can see that most clearly here. You see the fundamental frequency is the large peak. A higher harmonic is the smaller peak. And that's a signal that you've not got simple sinusoidal motion. Rather, you've got some more complicated, still periodic motion. So that's happened in that transition. On the right-hand side, I've got two values of alpha that are very close, within a couple of percent. One's 1.05, one's 1.07. These straddle that location we discovered at which the period of the pendulum, the frequency of the pendulum, the orbits of the pendulum kind of bifurcate, and you get period doubling. So alpha equals 1.05 is below period doubling. Alpha of 1.07 is above period doubling. Let's just look below period doubling first. Below period doubling, you see, if we look at the phase space plot, in red, all this red over here on the right is this transient period. In green is the period, the phase space trajectory in steady state. And the blue point here is the Poincare section points. They're all on top of one another. So in steady state, we've got a periodic non-sinusoidal motion, and we see that that is non-sinusoidal, but it is periodic in all of these harmonics. These are harmonics of the fundamental frequency. If we go to the plot below, it might at first sight look rather similar. We got a transitory period, that's the red trajectories. Then we've got this green oval, that's the steady state period. We got blue points, that's the Poincare section points. But there's actually two blue points, and there's two distinct ovals here. And this is period doubling. So for one complete period of this pendulum with this value of alpha, the pendulum's trajectory in phase space is first around one of the ovals, say the inner oval, and then around the other of the ovals, say the outer oval. The path through the Poincare section points through one complete period is first through one point and then later through the second point. So the period has literally doubled. That means in addition to the harmonics of the periodic motion, we should now, which are always higher than the fundamental frequency, we should now see a new frequency that's at half the driving force's frequency, because the period of this pendulum is twice the driving force's period. The frequency of this pendulum is half the driving force's frequency. And we see that. Here it's located. So here's the driving force frequency. We still see that, but we see in what was just empty space here, in the previous values of alpha, we see this new frequency that's half the driving force frequency. This is period doubling. This is a big effect. On the next four plots, I continue to increase the driving force parameter alpha. I've got four closely spaced values of alpha. I got 1.079, 1.080, 1.081, 1.082. And I'm just watching what happens in the frequency domain as I gradually increase alpha through this range. Now, this range, you might remember, corresponds to, we've already had one bifurcation. In this range, we get another bifurcation. And so in this range, we should see even lower frequencies in our data. And actually, that's what we see. So let's take a look at the lowest value of alpha. In the frequency domain, we see the driving force frequency, and we see this peak at half the driving force frequency. And we see in the full frequency distribution, a complicated series of peaks that correspond to the various harmonics due to the nature of the periodicity of this oscillatory motion of the driven pendulum. That looks similar in the plot below, 1.080, but in the plot below, there's actually also a frequency. It's a little hard to see here. Maybe you see the bump, the small bump, that's at 1/4 of the driving force frequency. And so this is the second bifurcation that occurs. And we met this in a previous class. We picked 1.079 and 1.080 to see where that second bifurcation occurs. We drew a bifurcation plot where we had a first bifurcation at somewhere around 1.06. That was one fork in the road. Then we had another pair that occurred between 1.079, 1.080. And that was the second pairs of bifurcations. And we now see an even lower frequency peak, 1/4 of the driving force frequency. This means that now, to complete one complete period, actually there are 4 distinct Poincare section points that you have to go through, and there are 4 distinct orbits in green that you have to go through. Over here on the right, I won't go through much details. We're above that second bifurcation. Once you're above that second bifurcation, the next bifurcations and the next bifurcations and the next bifurcations occur rather quickly. And you see the frequency spectrum getting increasingly complicated. You see the low energy region of the spectrum getting increasingly complicated as you get these additional bifurcations, as you're moving towards more chaotic behavior. On the last slide, I've got 4 more plots for 4 more values of the driving force parameter from 1.19 to 1.21. So just differing by a couple of % overall. You see, each of these plots looks quite different in phase space. So changing the driving force parameter by fractions of a % makes very different motion of the driven pendulum. And if you look in the frequency spectrum, you now see sort of a chaotic frequency spectrum. Take a look at the lower plots in the region around the driving force. You see rather chaotic frequency spectrum histograms, indicating that the data now comprises all sorts of frequencies. You've just got a continuum of frequencies in your data when you've moved into the chaotic region, which is this region here around alpha of 1.2. Anyway, those plots were examples of how you can use the Fourier transform and the frequency domain to explore the damp-driven pendulum. We saw the effects of the damping on the frequency of the pendulum. We saw then the effects of the driving force on the frequency of the pendulum, that as you increase the driving force, you get period doubling. We saw that occur. We get period quadrupling. We saw that occur. And then we saw the move to chaos. So Fourier transform, frequency domain, is a new tool, a very useful tool in visualizing, exploring damp-driven pendulum.